of the major challenge in the 21st century, which is the carbon neutrality or the so-called net zero carbon. I'd like to talk about the new design approach for the global carbon-based chemical and fuels toward the carbon neutrality. Okay. And the carbon dioxide has a greenhouse gas effect, which has been first reviewed by Savant Arrhenius, who is a Nobel laureate in 1903 in chemistry for his theory in the electrolyte dissociation. However, he was also an important pioneer in studying the greenhouse gas effect of CO2. In 1896, over 125 years ago, he published the first paper quantifying the CO2 effect in the atmosphere on the temperature on the ground. So today we know that the CO2 is a gas that actually absorbs the infrared wave, infrared light, and which is what causes the temperature rise on the ground. Technically, if I can make the pointer. So the CO2 molecule has a carbon-oxygen bond. The stretching of the bond actually creates infrared absorption, and this is what gets heat trapped in the Earth, and therefore causing the so-called greenhouse gas effect. And so the human society, they have caused the major increase in carbon dioxide concentration in the atmosphere. Over the last 800,000 years, the CO2 concentration has maintained an average of 260 ppm. The highest level over the last 800,000 years is 300 ppm. But over the last several decades, CO2 has increased dramatically to the concentration today that's over 420 ppm already. And the global temperature through the global collaborative studies and to measure the temperature, we know today that if the temperature has risen for about 1.2 degrees C from the pre-industrial revolution time. And this has caused a huge global concern for the global climate change. The reason for the CO2 issue is largely based on our current energy structure around the globe. The global energy currently is dominated by over 85% of our primary energy is fossil energy. That is coal, oil, and gas that came with the so-called dinosaur times, starting around 350 million years ago. And of course, since the first oil crisis in 1973 and the second oil crisis in 1979, the world has been doing a lot more research on enhancing renewable energy research. And today, renewable energy is an important part of the portfolio in the primary energy. But nonetheless, renewable energy, well, they are desirable. They do not come without problem either. One of them, as characterized by this cartoon picture, is lower energy density coupled with a seasonal variation, daily variation, and regional availability. So because of these issues combined, the world still relies on the primary energy supply over 80% on the fossil energy, which has a high energy density. And for the important industrial revolution, because of the way that we use energy over the last 200 years, it has caused important change in the global atmosphere, which one of the major things is the so-called CO2 concentration rise, along with other components such as SOx and NOx. In the last 10 years, there has been major global research on the global carbon budget, which is how much CO2 has gone up to the atmosphere, how much has been uptaken by the terrestrial sequestration or the land CO2 sink, or the ocean carbon sequestration, or the so-called ocean sink. So what we know from the most recent studies published by the international study, including 60 organizations in Europe, America, and Asia, we know the global carbon budget is such that every year over the last decade, we're adding 5.1 gigaton of carbon in the form of CO2. This is only measured in the amount of carbon in CO2, not the amount of CO2. those 5.1 gigaton of carbon is added to atmosphere every year in the last decade. And this has caused a major global climate crisis. And based on the recent studies in the Intergovernmental Panel on Climate Change, has noted that in the most recent report on the global warming of 1.5 degrees C, that if we want to reach the net zero emission by 2050, the current ambitious mitigation actions still are far from enough to reach the global target. And without options such as the CCUS, which means carbon dioxide capture, utilization, and storage, which is what we're going to get to. Over roughly about 15 to 17 years ago, the globe has become more interest in the CO2 utilization. So in one of the plenary lecture I gave in Norway at the International Conference on Carbon Dioxide Utilization, I wrote a review based on the plenary lecture on the global energy challenges and associated with the greenhouse gas control issue. Technically, the way we have the problem today is largely based on energy utilization, which is dictated by energy economics, policy regulation, and since the 1980s, environmental protection and environmental regulation, and since 1992, the global climate change. So by virtue of the greenhouse gas composition, greenhouse gas is largely dominated by carbon dioxide, although nitrogen oxide and methane are also greenhouse gases. So the CO2 control has become the major issue around the global technical as well as the political debate, which began with energy choices. As for example, we can use coal, we can use natural gas, and we can also use nuclear energy. If we go for nuclear energy, for example, we don't have CO2 issue. But on the other hand, CO2 issue is dominant because our primary energy is dominated by fossil energy, 80%. If we consider biomass energy, we also have a 5% of biomass, which is also CO2 releasing, although people ignore that part of CO2 since it comes from biomass. The next big issue is energy efficiency. Our current energy efficiency is only 35%, which means we waste 65% of energy to get the 35% useful energy out. And since the Industrial Revolution, we have released so much carbon into the atmosphere to stabilize the atmosphere CO2 concentration to avoid major catastrophic effect, CO2 capture, CO2 conversion, and CO2 utilization, along with CO2 sequestration, have become important and become central stage in the global research as well as the global discussion in the political arena. I will be mentioning some examples on CO2 capture and CO2 utilization, and coupled with some of the new design approach that we have been working on. I come from a very different angle, starting from about 3 decades ago, that when we were looking into the utilization of fossil energy. In 1993, I was invited by the editor of a journal of Japan Society for Energy Resources to write an article for the journal in the 50th anniversary for the society. And I actually wrote about one of my future dreams, where I stated the author dreams of the possibility of using CO2 from air and hydrogen from seawater to make liquid fuels and feedstock for chemical industry at some point in the 21st century. Of course, in those days, and this type of a statement have faced a strong resistance. And in fact, in the last 20 years, over the past 30 years, have always faced a strong resistance in the technical community that people think utilizing CO2 to make liquid fuels and chemicals are very unrealistic and only waste more energy. And that has changed in the last 10 years. And now I actually present a scenario for you. Why do I say so? And why the world should be moving toward CO2-based supply chain for fuels and chemicals. Because I've done analysis based on the global carbon cycle, starting from over 40 years ago, what we learned on the nature of a fuel formation. And so let me share with you, to start with, a well-known fact of the global carbon cycle. Global carbon cycle, technically, we all know that starting from CO2 and through the photosynthesis, we make CO2 and water into biomass. The biomass on land and also biomass in the ocean. And there are also animals on land, including humans and animal or the zooplanktons in the water in the ocean. And so when these organic materials or organisms and animals and biomasses, when they die, they become dead plant, dead animals. And typically when they decay back through aerobic decay into CO2 and water. So this is what the so-called global carbon cycle. It's going on every day and ever since the Earth was formed, when the green plant began to form and begin to die. And so this is the time in the dinosaur days, it happened all the time. In special region where we could have the so-called delta regions, there are certain places where we can cause accumulation of organic mass, especially when there's water burial in certain regions. And that causes sedimentation, followed by thermochemical and geochemical changes. In the chemistry, we call it diagenesis and catagenesis in the chemistry of the fuel formation. And that goes through millions of years to form what we call today as a fossil fuels, including coal, petroleum, and natural gas. Of course, when we burn the fuels, they simply return back to CO2 in the water. That means we're closing the loop in the global carbon cycle. Of course, we have been using CO2, using fossil fuels also in the chemical industry, the energy industry, through refinery processing to make fuels, chemicals, and organic materials. So that is what is considered a non-renewable fuels or non-sustainable fuels. Because of the nature of non-sustainable nature, we have also seen a major movement to make a sustainable fuel and chemicals starting from biomass. Of course, biomass growth takes some time. Depending on the nature, it takes months to years. If we are looking at a woody plant, it takes the order of 10 years to grow the wood or the trees before we can make use of them. And by collection, pre-treatment, and sending this into central refinery processing, we can make a biomass-based fuels and chemicals and materials. Of course, and that also depends on Mother Nature to first make the biomass in months or years. And so what we propose when I was writing the article in 1993 is that can we develop a new supply chain based on CO2 and water without relying on millions of years in a fossil fuel formation and without relying on months and years of a biomass formation, directly using CO2 and water to create a new sustainable cycle. So that is to make catalytic conversion of CO2 and water directly into fuels and chemicals in the order of a second. We can make that into second to meet the real world demand in the real world speed to production. So of course, CO2 and water does not carry much energy, so we have to bring energy into this process, and that has to come from renewable energy. So if we can achieve this, then we can indeed make CO2-based supply chain of fuels and chemicals, materials, and now there's no longer rely on fossil fuel consumption, and there's no longer rely on the biomass. Or if we consider that we cut all the tree to make fuels and chemicals, suppose we work in a city. If we cut all the trees in a city, it can hardly supply the fuel and energy for the city in a day, and yet it takes months and years to grow the biomass for the city or for the region. But if we can achieve the CO2 and water, then we can make that in real time. Of course, it costs energy. To put it in another way, that is, if we can capture CO2 from industrial sources or even from the air, and then using the hydrogen made from water or seawater through catalytic conversion, such as a catalytic hydrogenation reaction, we can make chemicals, make fuels such as synthetic natural gas, chemicals, polymers, or we can make a liquid hydrocarbon fuels to fuel the transportation, gasoline, jet fuel, and diesel fuels. If we can achieve that, that then can be called sustainable fuels. But of course, I'll be honest with you that many of my friends actually told me that, Junshan, you probably have nothing better to do than fooling around with CO2, because anything you do with CO2 only wastes more energy, and that translates into more CO2. Well, it has been willed that way for many years, but I'm used to that. But I kept working on that, and with our co-workers, with our collaborators, we worked on this for over 2.5 decades already. So coming back to develop the system, first of all, how do we capture CO2 more efficiently? Now, around the time that we were starting to work, CO2 capture was important, especially supported by many governments, in US government, for example. And the US government has published a report from the Department of Energy to say that CO2 capture is taking 2/3 of the cost or 3/4 of the cost of the CO2 sequestration, because it consumes so much energy, about 4 gigajoule of energy per ton of CO2 capture. So we face the first major problem. How can we lower the cost of CO2 capture dramatically? So the problem that we have with the current commercial process using liquid amine-based scrubbing. Again, I realize that not everyone in the audience is working in the chemistry area, so I won't bore anyone, but we published a book on CO2 conversion utilization 20 years ago. So we have been dealing with the chemistry and technology development, but just simply to put it in a way to make sense to everyone, why CO2 capture consumes so much energy. When I gave a lecture in Germany in BASF in 2008 in Frankfurt, and our friend from BASF publicized their industrial study, which represents the state of art still today, that current commercial process has a major energy consumptions to capture CO2. The first is because you use the amine solvent, heating up the solvent consumes 15% of energy. You heat up about 140 degrees C. But since you go above water's boiling point, water evaporates, which is a waste of energy, doesn't contribute anything for that matter. But you have to use that to make the process cycle. So evaporation of the water consumes 35% of energy. And desorption of CO2, because of strong chemical bonding, consume another 50%. So you put this number in 4 gigajoule per ton of CO2 capture. That's about 30% of electrical power generated from an electrical power plant. And that's why it's so energy intensive, expensive. So what did we do? We consider a new design which shift away from the conventional thinking. That is, we will not use the solvent at all. And we will not use the water at all. Therefore, we can knock out the 50%, knock out the 15%, knock out another 35%, and then for the desorption of CO2, we wake the chemical bonding to cut this 50 down to 40 or below. Therefore, theoretically, we can cut 100% energy consumption if we take this number down to 40% of the 100%. Well, can we do that? Of course, it's nice to say that, easy to say that, but it's hard to realize it. So what we did is we proposed a new concept, which is CO2 molecular basket adsorbent. And what everyone is seeing on this chart is my proposal chart in 1998, which I submitted to DOE, US Department of Energy, to propose this new way of energy efficient and compact CO2 capture process. And what we propose, we use a polymeric structure, something called polyethylene imine, for example. Polyethylene imine is a compound that we know. However, despite the fact that it can react with CO2, it does not capture any CO2 because there's no interfacial area. So in order to do so, we synthesize the nanoporous materials. And then we embed this polymer into this 3.5 nanometer channel. This 3.5 nanometer channel can then bond with the polymer branches to stretch this polymer out, just like a tree inside a channel. imagine that you pack apple or orange into a basket. Now we pack CO2 molecules into the basket because every tree branches in this polymeric tree can capture CO2. And by doing so, we can pack CO2 in a nanocase in high density. Therefore, we call this a molecular basket. And this is a picture of electron micrograph when we look at the CO2 molecular basket on the electron microscope. They are fine and nanoporous solid. Even with a 50% polymer loading, they look like a free-flowing solid. And when we do this type of CO2 capture using this molecular basket sorbent, we capture the CO2 in the amount which is an order of magnitude higher than the conventional solid materials, which is why the conventional materials are not economical for use. Another reason that conventional solid materials such as carbon or alumina or zeolite cannot be used is that they absorb moisture first before they can absorb CO2, so you have to separate the moisture. But we designed this material, they can capture the CO2 up to 10, 15 to 20% absorbent, and which is a CO2. So you can high capacity. Another important feature is that for conventional solid, you heat the materials, cool the gas down to room temperature. And for this material, we can run that at an elevated temperature, so we do not have to cool the flue gas down to very low temperature. It's in fact increasing capacity with increasing temperature up to somewhere around 80 to 90 degrees Celsius, depending on the nature of the polymer and also the nature of the materials. And so what we call this is thermodynamic and kinetic control in the two different regions. And we put different materials along with the commercial process into the same chart to compare where the molecular basket sorbent behave. But this is where the molecular basket sorbent behaves, and this is where the commercial system works. And to make it a long story short, and the molecular basket sorbent is 2 to 4 times better than any of the materials reported up to 2008 when we published this paper in the Journal of American Chemistry Society. So fundamentally, this is a result that was very encouraging to many people in the field. It caused a shift in thinking, also interest the U.S. Department of Energy to support or to develop a major pilot plant to demonstrate at the pilot plant level. Of course, we have done many different theoretical and mathematical correlations, and just to make sure that we know that how to predict performance and do the theoretical calculation. But I will not bore everyone down to the details in that. But to show you, this is a picture of our pilot plant where I'm sitting here along with my collaborators and also our industrial co-workers who actually built the plant for our project. And this is a 4-story high plant. I'm standing on the first floor. The top of the reactor is on the 4th floor. So we demonstrated this pilot plant, and starting from February 2015, the plant began to do the operation. Well, to give you a picture, so what we do in the laboratory, we use 1 gram or less. In the pilot plant, we use 150 kilograms of the materials to do the CO2 capture. So we successfully demonstrated this pilot plant, and then this pilot plant was dismantled and then taken to Norway and reassembled in a cement plant to actually test the flue gas not only from power plant, but also from a cement plant. Before we did this pilot plant, we first did a small pilot plant at the Pennsylvania State University in the small boiler demonstration plant. So we have demonstrated that. Of course, we also studied many different materials, different polymer structure to discover the absorbent material at different operating temperature and with a different optimum temperature for different reasons. Another important advance in our recent work in collaboration with our collaborator at the Dali University of Technology involving our PhD student is that we changed the structure of the typical adsorbent materials, which has a linear structure or linear pore structure, which is the typical SPE15 structure, first developed by Galen Stuckey at UC Santa Barbara, and also developed by Professor Dongyuan Zhao in Fudan University, SBA 15. And what we developed is an inverted cone-shaped pole structure, which is pictorially represented here. This is first synthesized by Professor Anfeng Zhang in our team, and then our PhD student Feijian Lou and associate professor Guanghui Zhang worked with us to develop this type of materials. As I can show you that this is the actual transmission electron micrograph. By using this inverted cone-shaped structure compared to the typical metal porous materials, we can make the absorption rate 50 to 60% higher, the desorption rate at 150 to 170% higher. So make it much faster in kinetics. And therefore, we can prepare our development materials for larger scale applications. So much for the CO2 capture part. Of course, there are global studies on the new way of CO2 capture and various approaches, including Alan Hayton at MIT, and who developed a new electrochemical CO2. And I talked to Alan in June when we had the International CO2 Conference at Princeton University. So next, let me spend a few minutes on the CO2 utilization. As I mentioned earlier, I had a huge resistance on CO2 utilization research. And until about 10 years ago, many people do not think positively about CO2 utilization, even in the technical community and scientific community. So it was a huge paradigm shift that was really needed for us to lead and promote the CO2 utilization. And this is a cartoon picture that I saw when I was a graduate student 40 years ago, and that which taught me a lot. And this was from a book by Professor Suyaki Kunitake. The meaning of the cartoon is really trying to train us, look at the thing from a very different angle. When you think you know something, look at upside down, or look at it from a completely different angle. So that if you look at the CO2 utilization from a very different angle, things begin to look different. And so there were quite a few years I have to tell myself that, well, concentrate on what you're doing. Don't care about what people say, negative things about the CO2 utilization. Well, of course, I was doing a lot of CO2 research in what I call Saturday and Sunday research, because nobody cares and nobody funds those type of CO2 utilization research for many years. But nonetheless, I believe in the value, as I will share with you why. Somewhat dynamically, CO2 is indeed lower energy, as many people believe why CO2 is useless, or why CO2 conversion is useless. It's because the belief that CO2 is so low in energy, and therefore anything you do with CO2 is a waste of energy. But those statements I guess that it does not consider the conventional or well-known factors we do that in chemical industry and energy industry of energy consuming chemical process all the time. Ethylene cracker is one example. Cement production is another example. They operate far below the CO2, so-called thermodynamic energy value. But nonetheless, because CO2 does not carry a price tag, and so that economically what people said makes sense. It just does not make sense when you think about the thermodynamic or kinetic when you really think about sustainable development, because all the fossil fuels were originally developed from the CO2. But on the other hand, if you think CO2 conversion toward the carbon neutrality, hydrogen must come from water. And therefore, for sustainable fuels and chemicals, CO2 and water need to be considered in both the energy and the processing requirement for the whole system. Now, what is the order of magnitude? That means it doesn't come for free. So the CO2 and the water react together. For example, if I calculate the thermodynamics, suppose we use CO2 and water to make a jet fuel, aviation fuel. It would consume 374 kilojoule per mole of CO2. In other words, if we want to convert a ton of CO2, we will consume 15.3 gigajoule. And if we want to make a ton of jet fuels, that will consume 47.5 gigajoule of energy. Now, how much of 7.5 gigajoule? Yes, just consider petroleum. How much energy does a ton of petroleum carry? A ton of petroleum carries 42 gigajoule. A ton of jet fuel carries 43.2 gigajoule of energy. So if we want to make a ton of jet fuel from CO2, you would need to consume 47.5 gigajoule. So that's a lot of energy. That means we have a major challenge in using the energy. However, can we do so? Suppose we use renewable energy. Can we do so? A lot of people say, no, you can never do that. But dramatic progress in the last 10 years have changed the global landscape. And lots of groups, including our own group, have done numerous research projects, and thanks to the hard work by our students and postdoc collaborators worldwide, and also research in many other groups, in industrial groups worldwide, we have seen what was viewed as difficult and impossible have become possible. First, due to the fuels. Now we can make CO2 into synthetic natural gas. We can make CO2 into LPG. We can make synthetic gas relatively easily. We can make methanol, ethanol, gasoline, jet fuel, and diesel fuel. And of course, CO2 is also used in enhanced oil recovery that's already practiced in industry, and particularly in Weyburn field. In North Dakota, CO2 capture shipped by pipeline to Weyburn oil field in Canada for CO2 EOR. For CO2 chemicals, we can do that, make CO2 into ethylene, propylene, butylene. These are the top 7 industrial organic chemicals, or methanol, ethanol, organic carbonate, acetic acid, also aromatic. Of course, in current industry, we already make urea, salicylic acid, and some specialty chemicals. In terms of CO2 materials, and now we can now make CO2 into functional polymers, and Covestro announced their commercial production of matrix for the bedding, matrix using CO2 synthesizing polyol, and the polyol is already in a commercial matrix production by Covestro, and other polymer materials from ethylene and propylene, of course. In organic, we can make a calcium-based carbonate or magnesium carbonate and construction materials, bricks, and either rolled polyethylene materials. And in the food industry, we already use CO2 for dry ice and small amounts of specialty chemicals. So I realize that people may not be interested in chemistry or the chemical technology, but I'll just show some examples to show we can do so. One example is from Sunfire company in Germany. They have built a plant to make the so-called blue crude. They announced a plan to build a semi-commercial or small-scale commercial plant in Norway to make the commercial blue crude that will be equivalent to 20 megawatt, producing 8,000 tons of blue crude. In fact, they just announced that the actual plant will become operational in Norsk in 2024. The production scale will be 25 milliliter in 2026. So the idea is using electrolysis to make water into hydrogen and CO2 reduction to turn CO2 into CO. And the third stage is using commercially proven technology called the Fischer-Tropsch synthesis to turn CO2 into liquid hydrocarbon fuels. In the R&D field, there are many different approaches.